Oh, you don't talk about
Okay, how are we doing here? So, what kind of space curve is this? Elliptical.
spiral.
Yeah, cylinder is a surface, right? A cylinder is a surface. So it's an elliptical. So the technical name is a helix, elliptical helix, but spiral is fine too. Okay, so elliptical helix or elliptical spiral. Okay, we want to find three surfaces that this curve lies on. So, what's one of the surfaces that this lies on, Brian? What's that?
Like the elliptical cylinder.
Elliptical cylinder. So can you tell me what the equation of it is? What's the, you
Let
can't.
X be anything, I guess.
What's that? Yep. Right.
Let X be anything.
Oh, so okay. So to get an equation of x and y, or equation of y and z. So that's yeah. So to write the surface as an equation of so basically that elliptical cylinder is a matter of what two variables? Y and z. So I guess you'd have maybe some like inverse sign or something like that, but we usually don't do that. Okay, so so that one is a little bit harder to write, but the other two, what's another? So let's just do that.
2 squared root of t squared minus 1, or 1 minus t squared.
What's that?
Would the equation be y equals 2 square root of 1 minus z squared?
Oh, right, of course. Of course. Yeah, so how would we find the surface associated with y and z? So if y equals 2 cosine t and z equals t, we're talking about what kind of curve, first of all? It's going to be a curve that's going to be generated through the x direction, right? So what kind of curve is that? Ellipse. And so we know how to write an ellipse. So we need to eliminate the parameter. How are we going to write that ellipse?
I'm going to solve for t for z equals sine of t since it's easier.
What you said before was right. That's not right. Don't solve for t here. Don't solve for t. How do we write this as an equation? Yes, sir.
So you could do 1 equals y squared over 4 plus z squared.
Right. So it's going to be based on our Pythagorean identity, right? We're going to do sine squared plus cosine squared equals 1. So this is a much easier example than the one we did in class last time, right? What is sine t? Z, right? What is cosine t? Y over 2. So this is y squared over, like he said. So if I were to graph that, what am I going to see? Do you know what I'm going to see if I do that? What am I going to hear if I do that? Angels. Okay.
So would it not be okay to evaluate for the positive and negative of cosine sine inverse?
It's not the natural way to do this.
No?
No.
Okay.
This is much cleaner, more natural. Then you don't have cosine, sine inverse have limited ranges, limited domains. This will work for all x values, all z and y values. So whenever we're parameterizing circles, ellipses, and then cylinders of those type, always don't use inverse sine and cosine. It's very limiting and very awkward. Yeah.
Where did you get the y squared over 4?
Well, what does cosine t equal?
Oh, okay.
See it?
2, 2y.
And then it's going to be squared, right? All right, so there it is. So there's so that would extend in the x direction, and so that spiral lives on that. What's this surface called? This is an elliptical cylinder, right? Elliptical cylinder, z squared plus y squared over 4 equals 1. Remember, if you have two of the variables, if you have an equation of two variables in space, that's a cylinder. The other variable just runs for all values, and you get a cylinder. Okay, what's another surface this thing lies on? Anybody? Yeah. How's that?
The cylinder y equals 2 cosine x.
And how'd you get that?
Well, if you let z be anything, then x is defined as t, and so you can plug in x at t.
Yeah, so if x is t, there's going to be some cylinder for x and y. If x is t, then what is y? So that's number one. Oh, this is number one. Number two is that y is 2 cosine of x. So that's a what kind of surface is that? What kind of? Okay, and so what kind of cylinder is it? Yeah, right. Sinusoidal cylinder. So look what happens when I look straight down on the. If you look straight down on the z-axis, so eliminate z, just look at x and y. What do you see? You see the function y equals 2 cosine x. Let z extend, and you've got that cylinder, right? And so that curve will live on that cylinder. Make sense? Okay, what's the other one? So there's one more surface this lies on.
Z equals sine of x.
Right, z equals sine of x. That's right. If I take away the y coordinate on this thing and look down the y-axis and just look at the xz plane, what do you see? You see y equals sine x. And so let y run, and you get that sinusoidal cylinder, z equals sine x. Okay, questions on that? What was the next question? Identify the blue, black, and red vector functions. Okay, what is the blue vector function then?
It's the vector that traces the curve.
Okay, it's the vector that traces the curve. So that's just our vector function, and that's the one that's given. T 2 cosine t sine t, right? T, that's what the blue one is. Okay. So two representations, right? So there's the representation of all the vectors that come out of that function, and those are all the blue vectors. But then when you put all those blue vectors as in standard position, it sweeps out the curve as you let t vary. Okay, so both this set of blue vectors and the green curve are both representations of that vector function. See that? Okay, what about let's go with the red. What is the red vector function?
Magnitude vector in each part of the vector function.
It's like a velocity function.
Okay, so if this were time and position, if t were time, and the vector function was a position function, then yes, it would be velocity. So that's a very common use application of these things, but it's not. Okay, yeah. So more generally than velocity, the red is what we call less than the derivative vector function, right? So if blue is the vector function, the green curve, then red is the derivative. And how do you know that red is the derivative function and not black? Yeah, so notice its value smaller here and larger here, and then smaller again here, and then larger again here. And remember, that's the magnitude of that vector is like the rate at which the curve is being swept out. for changing t. So where it's bending more tightly on the sides, less curve is swept out for the same change in t. And then at the top and the bottom, more curve is swept out for the same change in t. And so therefore, that's why that red vector's length is changing. Do you see that? Okay, so we got the vector function, the derivative vector function, that was the red one. And what? Let's write that. So what is that? What is that function? 1, -2 sine t, and cosine t. Agree? Yeah. So it's like finding a derivative vector function is kind of like falling out of bed, right? You just take the individual derivatives. There's nothing tricky about it. You just find the individual derivatives of each component, and that gives you the derivative vector function. Okay, so now the black thing is something new, but I heard that some of you kind of figured it out. So what do you notice about the black versus the red? It's not changing in magnitude, and what about its direction?
It stays in the direction of the red vector.
Same direction as red, but has a constant magnitude. What might that be?
The tangent vector.
Yeah, so this, okay, well this is a tangent vector too. This is tangent vector too. So this is called the unit tangent vector function.
Oh.
Unit, so it's unit because it always has magnitude of 1. Tangent because it's tangent to the curve. And vector function, unit tangent vector function. Okay, so that would be, that's called capital T. So what's its magnitude? Every vector in that vector function has a magnitude of 1. Okay, and so how would I write an expression to calculate that? What expression would calculate that unit tangent vector function? Now counter.
Take the derivative vector function and divide it by the magnitude of itself.
Oh, this was not right. What's wrong with this?
You put the position.
Yeah, I put the original. This should be r prime. If you notice that, good. That should have been r prime. So then the unit tangent would be, Connor?
Just the magnitude, or same as the derivative function, but divided by magnitude.
Right, so you're going to take the unit, you're going to take that thing and you're going to divide it by, so we're going to scale it by whatever its magnitude is at the moment of t. So it's always a unit vector. Okay, so what would it be? Can you write it? So can you write the function? So we can write it as a scalar multiple instead of writing it 3 times. So what would I write here? 1 over square root of 1 plus 4. Now, in the context of sine and cosine, I will often use just s and t when in this context of sine and cosine. It just makes things a lot nicer. So sine squared t plus. So can your mind adjust to that? Whenever we're doing lots of sines and cosines, I write s and t, and it makes life a lot easier. But I have it wrong. Let's see.
Wait, why isn't
It should be, yeah, squared. Square all 3 components, add them up, square root.
Can we put that on our exam? Like, you'll know what that means if you put that on.
Well, since the exams are all multiple choice, I'm not sure
Oh, okay.
I'm going to do that.
Nice. That's what
But
we
yes,
do.
whatever I do in class, unless stated otherwise, you can do for assignments and tests. Okay. So let's talk about, let's take this to the next step here. So suppose I have a space curve, just generic. Okay, and so this is, say, r of t. This is my vector function r of t, and it's a curve in space, we know that. And now I have, say, at this point right here, we have this vector called the unit tangent vector, and using the numbers on the clock, which direction will the unit tangent vector point, approximately? Right here. So like noon, like 12 o'clock, 3 o'clock, 6 o'clock. You should be thinking 2. It's about 2 o'clock. This. And the magnitude of that is 1, right? And so that's going to point in the direction of the curve. And tangent to the curve right there. Okay, so what would... There's another function that's this. We take the derivative of that, and we make it a unit vector. Let's talk about what that would mean. Okay, so what would that mean? So the derivative of the unit tangent vector, all the unit tangent vectors have magnitude what? 1. So if you're talking about the derivative or the rate of change of that, what is that talking about?
The rate of change of the actual vector.
But if its magnitude is always 1, then the rate of change of this would be... No, it's a vector, guys. It's a vector. So the rate of change would pertain to what? Yeah, so yeah, the direction, right? So if the magnitude is staying 1, then the rate of change of the magnitude, you're right, is 0. But vectors have direction. So let's investigate this. If I had, say, suppose this vector was at t equals 3. Okay? Suppose little t. Little t equals 3 gives me that point on the curve. And so there's my t of 3. So now I want to think about little t being 3.01. So little, and the curve is oriented this way. Remember, parametric curves have orientation for increasing values of the parameter. So for increasing t, we go this way. So what would t of 3.01 look like, capital T? The unit tangent vector at 3.01, what would its direction be? Would it be more shallow, like more towards 3 o'clock, or more steep, like towards 1 o'clock? Yeah, you should think it's more shallow, like more towards 3 o'clock. Okay, so if I were to draw that tail to tail, t of 3.01, it might be something like this. Still a little bit up. I don't want you to think it's horizontal. It's not necessarily horizontal. So what's the change in the t vector from 3 to 3.01? What's the change? How could we represent that? No, like represent it physically here. What's that? No, the change from here to here. How do we calculate change in general? Final minus initial, right? And so final minus initial when it comes to vectors would be like vector subtraction, right? It'd be like this vector minus this one. So what vector would that be, pointing up or down? Down. Final minus initial will be this vector right here. So this is like kind of like d t vector, right? It's like the change in that t vector as you let the parameter little t increase a little bit. So what is that showing about? And then we're going to take that and we're going to make it into a unit vector. So we're going to take that direction right there and make it a unit vector. So what is that showing? Let's do orange. So that would be like this right here. So I got the direction is kind of like maybe what, 5 o'clock? It's like 5 o'clock. What is that showing about the space curve at little t equals 3? Let me redo that. Do better than that. There we go. Wow. I know I can do it. All right, there we go. That's a good one. What is that showing then about, it's like the change in direction, right? It's like the change in direction. And it's pointing kind of like in the 5 o'clock direction. So it's showing what about the curve as points are generated. So it's showing how the capital T function is changing, or it's showing, and what's changing there? The magnitude isn't changing, the direction is changing. So it's how the direction is changing, or it's like the direction of turning. If you're in the car, are you turning left or right here? Right. Turning right, and so this points straight to the right. See that? This is called the unit normal vector. The unit normal vector is normal to the curve, right? Do you see that it's orthogonal to the tangent? And it's purely showing you the direction of turning. Because if you were heading along that curve, it's turning to the right, it's like the direction is straight out the passenger window to the right. Doesn't matter how hard you're turning to the right. If you're just gently turning to the right, it's still straight out the passenger window. If you're turning super hard to the right, it's still straight out the passenger window.
So they should always be perpendicular to each other?
Yes, it will always be perpendicular, right? And do you see how that kind of worked out? If you imagine the next little t vector that's going to be perpendicular, the difference, that little vector right there, that shows how much the difference between the final and the initial is going to be orthogonal to the first one. So that's my n vector. Okay, so here's your t vector. So imagine taking the derivative of this, which now you have three quotient rules with sines and cosines and a square root, so with chain rule in the denominator. See that? So you have quotient rule with chain rule, quotient rule with chain rule, quotient rule with chain rule. And then you're going to unitize that and divide by the magnitude of that. It's really awful. So I think you just will have maybe one web work problem and one written homework problem where it's rigged pretty nicely to help you. Okay? So you'll just pay your dues one time and then that's it. I don't care about that. I don't care about all that algebra, but just know what's happening here. Here's your t. You're going to take the derivative of that, which is pretty awful quotient rule, and then you have to find the magnitude of that and divide. So I'm much more interested in the concept of the unit normal vector, and we'll do some examples in class today of figuring that out just geometrically, like using reasoning rather than algebra, okay? Much more interested in that. Okay, and then there's another vector. Okay, so if we there's another vector called, that we get by taking t and doing the cross product with n. Yeah.
So for the unit normal vector,
Uh-huh.
if there was no change in that t of t, would it be 0 or would it be facing the same direction as the unit tangent?
So you got to have a change in t, a little t. I think what you mean to say is if it's straight.
Yeah.
Yeah, if the curve is heading straight, then the unit normal is 0.
Okay.
There's no, it's the zero vector. There's no, it has no turning, so the vector is 0. Another question?
No, I was doing right-handed.
Okay, sure. Okay, so tell me.
Well, I was like we're dot producting it, so it's
Cross.
Yes.
Yeah.
So like I was pointing it like firstly in the direction of the t vector, curling my fingers in the n direction with my thumb pointing into the screen, giving us the vector that's going to result from this cross.
So he's saying that the direction of that. So first of all, the magnitude is going to be 1 again, and we're cross producting 2 vector functions whose values are always 1. We're going to get a vector function whose value magnitude is always 1. So it's really again about direction. So he's saying into the screen, according to this picture. She agrees. So should it be into the screen or out of the screen? So yeah, if you're thinking into the screen, that's right. You take your right hand, you're pointing in the direction of t so that you curl your fingers towards n. So where is it? How is it that it's here that I would curl my fingers towards n? Do you see that? Into the screen, okay? This is called the we should have given him the color. Let's go to the color. What should be blue? This is called B of t. It's called the binormal vector. Don't die. So what you have then with these 3 vectors is as little t increases and like generates points on the curve, you have like a little R3. This is like a little R3 coordinate system that moves along the curve. Can you imagine that? So like I'm using my thumb, index finger, and third finger as like a R3 coordinate system. And so, get this right here. Yeah, so like this. So then as t increases, that R3 coordinate system moves along with the curve so that the t function is always pointing the direction of the curve, n is always pointing in the direction of turning, and then b is orthogonal to that plane. Okay, so this brings up, so with that little R3 coordinate system, you have planes that have characteristics relative to the curve. So like which 2 vectors would form the plane that's orthogonal to the curve at that moment? Which 2 vectors would form the plane orthogonal to the curve at that moment? He wants n and b. He said n and b. Agree with that? Right. That's called the normal plane because it's normal to the curve. But notice, which vector would you use to define that plane if you were going to write its equation? Which would you need to write its equation? T. So the normal plane doesn't use the normal vector because normal vector is in the plane. We need this to come back. Please. Yes, okay. So yeah, so to write the normal plane, which is parallel to n and b, you would use the tangent vector to write its equation, because it needs to be orthogonal to the plane, right? All right, so then there's the tangent plane. So which 2 vectors would be in the plane of that's tangent to the curve at that point? People are saying b and t. Agree with that? Tangent. So tangent is b and t. The tangent plane would be b and t. No, it's b and t. Trust me. So n and t is different. N and t is not tangent to the plane because we'll get to that in a second. B and t is the tangent. So this is coming up like this. B and t, it comes up and it's tangent, right? It's tangent to that plane. So which vector would you need to write the equation of the tangent plane? N would be what you would need to write its equation. All right? So So this other plane, n and t, it's not a tangent plane. It's different. So, for instance, if you took a little teeny bit of the curve, like if I so from 3 to 3.01. So imagine that little piece of the curve right there. Really small piece of the curve. The tangent plane is like tangent to that curve. But the plane of n and t, it like contains the curve at that moment. Do you see that?
Yeah.
So for 2 points really close together, both of those points would lie in the plane of n and t, but not in the tangent plane. So that plane of t and n is called the osculating plane. And it's the plane that the curve is in at that moment. It's not tangent to the curve. It's kind of like the plane that the curve is in at that moment. The curve is kind of, the plane kind of contains the curve just for an itty bitty change in t. That's called the osculating plane. So we got I got a chart I'm going to show you in a second with all that information. So which of the three vectors defined or is used to write the equation of the osculating plane? That'd be B, right? That'd be B.
So the osculating plane, the curve isn't allowed to go out of the oscillating plane, right?
You got to take a small enough change in little t so that it's virtually creating a plane. Like like that little piece of the curve creates a plane, and then the osculating plane it's like the curve, the plane the curve is in at that moment. So if t changes, it's out of that plane. But I'm saying if t changes just a tiny little bit, it's that plane. Because if you have a curve, if you have a piece of a circle, that defines a plane, right? So if they have a small enough change in little t, it's like you have a little teeny segment of a circle. It's the plane of that circle. Does that make sense? Yeah. Okay, so let's just summarize that here. Okay, so for time's sake, I'm not gonna, if you would get the video, go to the video to copy this down. But the normal plane, its relation to the plane is orthogonal to the curve. The two vectors that form that plane are b and n. And then what vector is used for its equation? T. Okay, then we got the tangent plane. That's tangent to the curve. And the two vectors that form that plane are b and t, and the vector used for its equation is n. And then the last one is the osculating plane. Its relation is, it's like the plane the curve is in at that moment. It's formed by n and t, and it's the vector orthogonal to it that you would write this equation with as b. Okay, so I want to get to an example. So any questions about that? So you have the three vectors and the three planes, and as you move through the space curve, it's like that R3 coordinate system moves along with the curve. So that t is always pointing in the direction of the curve, n is always telling you the direction you're turning, and then b is orthogonal to both of those, or orthogonal to the plane that the curve is in. So yeah, like if you're driving on a flat road, then the b vector is either straight up or straight down. Does that make sense? So t is straight out the front of the car, n is either right out the passenger side or right out the driver's side, and then b is either up or down, depending on which way you're turning, or going forwards or backwards. Cool, so another example here. Same, slightly different. I got t, 2 sine t, and negative cosine t for this one. And I want to show more of it here. Okay, so I'm showing 4 vector functions here. 4 vector functions, and hopefully you can distinguish the colors there. I got pink. Let's see, alphabetical order. Black, blue, pink, and red. So I want you to identify which vector function it is.
Well, the derivative, right?
Okay, so which vector function is the source vector function, the green curve? Which one is that?
Brian, is the actual curve.
Yeah, the actual curve or the source vector function for all this is the red one. Okay? What about the unit tangent? Where's our unit tangent vector? They're saying pink. Do you agree? Pink. Okay? What about our unit normal? I heard blue and black. So let me, if I look this way, I think this clears it up. Blue or black? Blue. The blue one is always showing the direction of turn. It's like it's like always turning left, right? As you go around the spiral, if you were driving in your car, you're always turning to the left. So then the normal vector would be pointing straight out your driver window, straight perpendicular to the way you're going. And that leaves the black vector, which is, that's the binormal. So we can see that a little better this way probably. Do you see how it's perpendicular? That's a good place right there. Do you see how it's perpendicular kind of to the plane, like right there? That's a good shot of the binormal vector. So right now, if you had to pick a plane that the curve was in, it'd be like this. See that? So like if you took a little teeny bit of curve and thought of that as a circle, there's a plane for that circle, right? And this is orthogonal to that plane. It's the plane that the curve is in at that moment. Okay, so now let's actually find those. Let's use some reasoning rather than a lot of ugly algebra. We're going to find all those vectors there at, right there, at 0. I can do it. Stay. There we go. Okay, so see that point right there? That's for t equals 0. So first find the coordinates of that point, or the red vector. So we're going to do t equals 0. And then we're going to use reasoning about what we know about these vectors to write them, rather than going through all the algebra and plugging in 0, right? So we could go through all the algebra and get those vector functions and then plug in 0. But since this is a kind of special case, we can instead, just take what we know and kind of reason it out. All right, so at t equals 0, what's the red vector? That's the actual curve. So what's the red vector? What's the pink vector? What's the blue vector? And what's the black vector? Give it a shot. See what you can come up with. And I'll give you different views here, okay? There's a top view. Now, so we might have to do some math, okay? We might have to do some math. That's okay. So however you can do it, however you can find these 4 vectors. All right, so what is the red vector? 0, 0, -1, and that should make sense. And that's what you get when you plug 0 into our function. So r of 0 is 0, 0, -1, and it looks like that, right? It's pointing straight down. and it's what you get when you plug 0 into the function. Okay, and let's do I think the unit normal is easiest next. What's the unit normal at 0? Some people are saying 0, 0, 1. Agree with that? What direction is it pointing?
Straight up.
Straight up. What's its magnitude? 1. Therefore, if you said 0, 0, 1, you're correct. Okay, how about the unit tangent? Which one was that, pink or black? Pink. Okay, so notice that it's kind of at a... It's not at a 45-degree angle, so we're going to have to do the math here. So how would we find the unit tangent? What would we do? Take the derivative. Derivative is 1, 2 cosine t, sine t, at 0. 1, 2, 0. So is that n? Or t, I'm sorry. What would you need to do? So we got the direction. It's 2 in the y direction for every 1 in the x direction. So we just need the unit vector for that. So t would be 1 over root 5, 2 over root 5, 0. Last thing here. So now what about, we have some choices for finding b of t. What could we do? We could do the cross product. We could do, and this is easy because we're at a particular value. We're not working with the functions. We're at 0, so it'd be easy to do the cross product. But there's another way that's easy here too, besides doing the cross product. I know that we're over, sorry. Notice that, what's the relationship between b and t? Orthogonal, right? If this is 2 to 1, and then they're orthogonal, then what does this ratio of components have to be? 1 to 2, right? It's pretty cool, right? So yeah, opposite reciprocal. We know that the dot product would have to be 0, so these have to be switched, and then these are in the same direction, but these are in opposite direction, so that would give us a dot product of 0. So we can just write it down. What will it be? Now notice that this is what? The positive x is here, positive y is here. So our x coordinate would be positive 2 over radical 5. Y coordinate would be negative 1 over radical 5 and 0. So that's what I mean by kind of reasoning about that. Come on. Come on. Why? Because the tangent plane is parallel to the xy plane. So both the tangent and the binormal vectors have z components of 0. Because our tangent plane is horizontal. So that's why its component is 0.